Hey, Phil from Mux here. Thank you so much for joining me at Mile High Video. This is, I think, my third talk at Mile High Video over the last couple of years. Hopefully you'll enjoy it. It's titled, Traversing the First Mile is Harder than Traversing the Last Mile. Let's get started. So first, a little bit about me. My name's Phil. I'm a streaming architect at Mux. I've been at Mux for a little over 2 years now. Outside of my day job, I also organise a London Video Technology meetup, and I co-organise Demux alongside Matt McClure. I co-host the Demux podcast, and I've been in the video industry for about the last 10 years, including Bright Cove and the BBC. At Mux, we build two products, Mux Data and Mux Video. Mux Data is a best-of-breed live and on-demand streaming analytics tool, which gives you QoE information about what your viewers are experiencing, used by companies like Fox and CBS on the Super Bowl. We also build Mux Video, which is what I'm going to be talking about today, which is an API to allow any development team to build amazing video experiences. But 2020 really has been all about live video. We've seen a huge growth in live minutes ingested into Mux during 2020, and this trend is continuing now, and we also expect this to continue into 2021 as well. Now, what's super interesting is our live customers range from very high quality content studios, places like SoulCycle, and complex remote productions, things like Hopin or Demuxed Indeed, or things like the DPP Tech Leaders Briefing, which came out of a White Light virtual studio, all the way over to $150 Android phones using Larix Broadcaster. On my desk, I've got a Nokia 5.3, which is an awful lot of phone for $150. It's got 4-5 cameras in it, a great processor, it'll do 1080p streams really quite well in well-lit conditions, and tons of CPU and storage to process those streams as well. And that's particularly relevant because 2020's growth market is different. 2020's growth market is personal trainers, yoga coaches, teachers, professors, DJs, and comedians, people who weren't live streaming 12 months ago. And in our case, they're all using RTMP. And why RTMP? Well, other than it being the ingest technology that we support, it's ubiquitous. Pretty much any piece of hardware or software that's used to create a live stream supports RTMP outputs. Lots of free and open source software and freeware apps can create it, right? We've got OBS on Windows, Linux, macOS, completely free, great vision mixing studio. Larix Broadcaster on iOS and Android, a fantastic, powerful app that can create RTMP on mobile devices. It's also a very well understood protocol. This has been in production for over 20 years now. The spec's actually almost been open for 20 years, coming up in a couple of years' time. And it actually works pretty well under controlled network conditions. But the challenge here is RTMP is fundamentally TCP based, and TCP is connection oriented. So RTMP doesn't handle connection drops within the protocol, it can't. So what do you do when a connection drops? Well, you pretty much just try and reconnect. And that's the first thing we're going to look at today. We're going to look at a bunch of interesting or special RTMP and TCP disconnects from real-world examples during 2020. One of the themes of 2020 from a connectivity standpoint really has been good internet connections turning bad. This is one of kind of the classic examples we've seen over 2020 of streams that come up, stream completely stably for a while, and then just go wonky, to be honest. In this case, we saw, I think it was after about an hour of this stream running, the RTMP connection dropped, but as soon as it reconnected, we had a bad stream after that. So the bitrate was all over the place, the frame rate was all over the place, and when we dug into this after the stream had ended, we discovered that a backup process had kicked off. I think it was even just a Dropbox sync on the user's network, which started consuming internet connectivity, brought the RTMP feed down, and then when it reconnected, it was fighting for bandwidth alongside that backup process. But beyond that, we also see bizarre QoS modes across networks, and especially corporate networks. Now you might say, hang on, 2020, corporate networks, I thought we weren't in office spaces. Well, what's interesting there is people are actually using their offices to do their live streams because they're empty, so it's actually easier to social distance there. Now, this is an interesting example where a live stream that was actually also chugging along quite happily suddenly started experiencing periodic TCP disconnects. I think it was every 5 or 6 minutes on this stream. And when we dug into this, it turned out that it was just a network policy on that corporate network that, hang on, you're not allowed long-running TCP connections. That's not something that we're designed to do. But this doesn't just happen in the home. This happens between clouds as well. So inter-cloud traffic totally also suffers from internet weather. For example, AWS to Google Cloud just isn't 100% reliable. And this happens because people build on top of tools like FFmpeg or GStreamer running in a cloud instance and pushing into our RTMP endpoints. And some of the use cases there are things like Cloud Vision mixers, which is ever more common in a remote production world, or pre-recorded movies and live streams that you want to kind of look like they're live but are actually pre-recorded. Very common in 2020. And then there's a couple of silly ones. Now, I must admit I did pull this photo off of Quora, I think it was, but I've actually lived somewhere that had their Wi-Fi router on top of their microwave. And yep, every time you turn the microwave on, funnily enough, your packets would kind of disappear into oblivion. But just in general, unmanaged home Wi-Fi networks are not the best place to live stream. But, yeah, some networks are obviously better than others. And this one actually came in while I was writing this talk. A customer who was complaining that a client of theirs had a bad experience on a bad hotel Wi-Fi network. And this wasn't someone watching on a hotel Wi-Fi network. This was actually someone streaming an RTMP stream in from a hotel Wi-Fi network. And what's interesting here is this doesn't just end at the first network or into cloud traffic. This can be a challenge on your load balancers as well. So load balancers generally aren't actually built for long-running TCP connections. They can all occasionally just drop all your TCP connections, and sometimes that can be over a really short period of time. And this commonly happens during scaling events, for example, where they need to reshard traffic. And this is common across kind of all of the cloud load balancers you have available to you today. So what can you do about this? Well, maybe you want to run your own RTMP edge. Now, this isn't actually that hard. It's pretty easy to deploy Nginx RTMP to a bunch of regions and use DNS traffic to load balance between different instances. You can then either backhaul your RTMP traffic over known good network links or just encode locally at that RTMP edge. Now, the problem is obviously, oh god, now I have to kind of run and manage my own RTMP edge. And one of the biggest challenges there is that removing nodes and spinning them up and down is really hard when you've got active live streams. You need those streams to be down from an RTMP perspective to be able to rebalance that traffic. But what I'm really saying is disconnects are still going to happen on the first mile. So what can we do about it? Well, we pretty much just have to wait for the reconnect. And what can we do while we're waiting for a reconnect? Well, there's a couple of common options. We could just end the stream instead. Well, just issue an end list, which is probably statistically not right. We could display a slate, say, hey, sorry, technical difficulties, or we could just leave the users rebuffering. And this really becomes a question of how do you know when a stream is stopped deliberately versus just a disconnection? One option is to use the RTMP unpublished message. Now, this is sparsely supported in some encoders, particularly cheaper ones, open source ones on mobile applications. But also in a lot of cases, you have to be very careful about how you pick up on certain hooks of closing applications. For example, when you force close an app on your iPhone, a lot of people might not listen for that event and cleanly send an unpublished message. You could assume every disconnection is a stream end, which is statistically probably a wrong assumption. Or you could expose an API, but you'll probably find that most customers don't actually bother integrating with that. Our approach for this, we call it reconnect windows, and we hold the user's buffering for a period of time, hoping that the RTMP source reconnects. For us, we allow this to be configurable from anything from 1 second to 5 minutes, and then we add an optional API to signal the stream has ended if you don't want to wait for that period to elapse. Now, what's interesting here is you have to think a bit about, well, how long is it actually going to be while my viewers sit in this buffering state before they abandon the stream or refresh the page? And honestly, it's not long before your users abandon the stream. And this causes a lot of rebuffering. Here's an event we actually had during Demux this year where one of our encoders crashed and hey, we held everyone in a rebuffering state for a while. But in my mind, what's really interesting here in 2020 is that the first mile and the last mile have now become the same networks. Now, QoE and QoS are kind of solved on the last mile though, right? On the last mile, we are using short-running HTTP requests, and the chances of the TCP connection that underlies that HTTP request breaking mid-request is relatively rare, but we also have a bunch of technologies built into our players to retry those HTTP requests in the case of these connection failures. We also have a variety of technologies to help improve last mile resilience, things like multi-CDN, redundant streams in HLS and Dash. But what tools do we have for ingestion of streams? And what I'm really saying is it time to replace RTMP? Now, over the last couple of years, we've really had this new rise of newer UDP-based, in general, ingest transport technologies that are kind of getting ready to go now. Things like RIST and SRT are newer open standards, and ZigZee is slightly older but commercial standard. And free and open source and freeware tooling is really catching up here. Things like OBS supports SRT destinations now, and GStreamer supports both SRT and RIST destinations. And the commercial tooling is adopting standards like this too. For example, Larix Broadcaster on my $150 Android phone already supports SRT and RIST as well. So I'm not going to spend a huge amount of time talking about these protocols. Kieran's already talked about them quite a lot this week, and he's a lot more of an expert on this than I am, I'm not going to lie. So SRT is Secure Reliable Transport. It's a specification that was kind of reverse engineered from a proprietary Haivision protocol by Haivision and Wowzer and is now obviously open to integrate. It's super easy to integrate and get started with. It's got a great open source implementation, libSRT. It's actually based on UDT, which is a UDP-based file transfer technology. It uses ACK and NACS for retransmission. And it kind of has this constant latency concept, and you select how long you want your latency to be for a trade-off against how much packet loss you can deal with and how much bandwidth overhead you might need. I'm going to talk about kind of performance just in terms of packet loss, because it's the easiest number to kind of absorb, but it remains stable at about 10% packet loss if you have 100% bitrate overhead available to you. To contrast with SRT, RIST, Reliable Internet Stream Transport, is based on RTP and RTCP, which are more traditional video technologies. Has a couple of different profiles with different features on them. It's based on just NACS, but it does have slightly better performance than SRT does. So it's stable at 20% packet loss at 100% bitrate overhead, and that can be pushed even further to 35 or 40% if you have a lot of overhead, to about 200%. Now, SRT and RIST actually have a common problem here. So with RTMP, places like Mux and Twitch just give out kind of one set of host names and route based on stream key. But these sorts of approaches are much less complete in SRT and RIST. So RIST has an SSRC and a passphrase embedded in the main profile, which is one way to achieve this, and SRT recently introduced a stream ID concept, which is their kind of approach for doing this. Commercial tooling is slowly starting to address this, but this stuff just doesn't really quite exist yet in these ecosystems. But taking a look at the bigger picture, the growth industries during 2020 aren't actually technical users, these comedians, these DJs, these fitness instructors, these teachers. For them, configuring OBS or Wirecast is even a challenge. They sometimes forget to quit their encoder after a live stream ends, which best case is expensive and worst case is pretty embarrassing. And people sometimes build mobile apps, native mobile apps, to help address this, but they're expensive and time-consuming to develop and deploy. But these people, for the most part, do know how to use a website. So what these people really need is to be able to go live from a browser. But none of these new technologies really solve that problem. And lots of untechnical users need this, and lots of businesses want this to accelerate their product development. So maybe a lot of people have started using WebRTC as an ingest technology. Well, it's not really designed for that. WebRTC is designed for real-time communication, and it makes sacrifices on quality to achieve latency. It's not optimized for high-quality ingest. So maybe we could use WebSockets as ingest technology. Even we've got some prototypes of doing this. Well, unfortunately, WebSockets kind of suffer from the exact same problem that RTMP does, which is that they're long-running TCP connections. So it's kind of all the way back to the start of this presentation again. So where do we go from here? Well, we kind of still don't have that new ingest protocol that works for this always ready to stream use case and this streaming from a browser use case. So maybe we need yet another ingest protocol that kind of matches more closely onto the UGC use cases. Maybe that's HTTP3 and datagrams. There's a lot of discussion of that. And you can already see places like Instagram and Facebook moving in this direction and doing things over H2 and quick. Or, from Unified Streaming's talk last year, why not just post and put chunks over HTTP instead? If HTTP is good enough on the last mile, maybe it's also a good solution for the first mile. So, in conclusion, over the last 15 minutes, hey, RTMP is a headache and it's really hard to scale on modern cloud architectures, but as of today, it still is this necessary evil. COVID has really changed how we see patterns and causes of disconnects on our network, but also on first mile networks around the world. Building your own RTMP edge does solve some of these problems, but it is complex, it is expensive, and you will still need things like reconnect windows or slating to deal with some more complex problems. New protocols like SRT and RIST aren't yet drop-in replacements if you want this true multi-tenant environment. And maybe something like HTTP3 can help us. But what I'm really saying is, hey, maybe we need yet another ingest technology. Here's a couple of resources I used when I was putting this together, but also other things to go watch if you want to get more into depth on any of the topics on here. And with that, if you have any questions, I'd love to hear them now, or you can reach out to me on phil@mux.com. Thank you so much for having me. Have a great day.